Okay, so for this video we've got a question. A racing car passes the finish line of a race moving at a constant velocity of 60 meters per second. After 5 seconds, it starts decelerating at 3 meters per second until coming to rest. Sketch the displacement time graph for the motion after the end of the race, measuring the displacement from the finishing line. So we can start now. So if we're measuring displacement from the finishing line, what this means is that when you're at the finishing line, the displacement is going to be 0. So if that's the finishing line, the displacement needs to be 0. So we're starting out there when we cross the finish line. So it's moving at a constant velocity of 60, and it does that for 5 seconds. So 60 meters per second for 5 seconds. So we need to figure out how much distance will it cover to get there in those 5 seconds. So we're going to use the SUVAT equations, SUVAT. So we need to find the displacement. So we've got the time, 5 seconds. We've got the velocity, 60. What else do we have? Well, we also have acceleration, because when you have a constant speed, that means your speed is not changing. So you have an acceleration of 0. And we need to find S. So we can use S, U, A, and T. We can ignore the V. So we'll have to use S equals UT plus a half AT squared. What next? S equals 60 times 5 plus a half times 0 times 5 squared. A half times 0 is 0. 0 times 5 squared is 0. So this whole thing is 0 plus 60 times 5, which is 300. So displacement is going to be 300 meters. So right there, the displacement, we're going to be somewhere like at 300. Maybe somewhere there. Let's put it as 300. So constant velocity, we must have a straight line, and we're going to do it up to 5 seconds. So it should be something like that. So the straight line shows that we're moving at a constant velocity. Then it says after 5 seconds, we start decelerating at 3 meters per second until we come to rest. So we're going to use a different SUVAT equation here because the acceleration has changed. It has changed from 0 and it's now a 3. So let's see what we can do for that. So right, we have the acceleration as 3 now. What else do we have? It starts decelerating at 3 meters per second squared until it comes to rest. Coming to rest means that the final velocity should be 0 because you're not moving then. And then what will be the initial velocity? So we're looking at time 5. What's the initial velocity there? Well, the initial velocity there is actually going to just be 60, because for the first 5 seconds it's moving at 60 and then it starts decelerating. When at the moment when it starts decelerating, it was still moving at 60 and then it starts slowing down from there. Now, how do we draw this then? We need to first think about this. What does decelerating mean? Decelerating means that the speed is gonna reduce. What is the speed represented by on a displacement time graph? It is actually represented by the gradient. If you have a constant speed, you have a constant gradient. So something like a straight line, any straight line. If the gradient is changing, you need to have a curve. So if the speed is reducing, that means the gradient must be reducing. The steepness must be reducing. So you can look at this. This is the high gradient. That's even a higher gradient, and then this is a low gradient. So we must be coming, if we're decelerating, we must be coming from a high gradient and then going to a low gradient. And if we are coming to rest, rest means 0 speed or 0 gradient, and 0 gradient is just a straight horizontal line, something like that. So we are coming from something that looks a bit steep, and we're gonna go and make it less steep. Let me just draw this again, like that. Okay, so we're at time 5. So at time 5, we're gonna just continue the line a bit, but we're gonna like make it less and less and less steep, just to show that basically the speed is reducing. So you can see right there, the gradient was a bit high, then there the gradient started reducing, and then there the gradient is 0. So that helps us see that the speed is reducing. So now we need to figure out the time at which this object actually comes to rest. What time is this object actually gonna completely have stopped moving? So let's try to calculate that. So we're gonna use the Suvart equation again to figure out the time at which it comes to rest. What's the acceleration? Well, they're saying it decelerates 3 meters per second. So, but instead of writing a 3, because it's deceleration, we're going to put a minus 3, like that. And then we want the initial velocity, we said it's 60. And then coming to rest means that the final velocity is 0. Actually, I had already written that. Now we can calculate the time. We can use the equation A equals V minus U over T. We can interchange the T and the A so that we have T equals V minus U over A, which is 60 divided by 3. Negative 60 divided by negative 3. I missed a step. To be 0 minus 60 divided by negative 3, which is negative 60 divided by negative 3, which is 20 seconds. So this is how long it takes to get from a speed of 60. Speed of 60 was at 5 seconds there. Now you need to be quite careful about this. This is how long it takes to get from a speed of 60, which was somewhere there, to a speed of 0, which is when it's completely flat. So this time here is 20 seconds. But you can't just come and label this as 20. No, this must then be 25, because 20 is, the 20 seconds come after the 5. So it's 5 plus 20. The 20 seconds were the time taken to slow down. Now we need to also figure out the displacement at that time. So we're going to use another equation to figure out the displacement. So we can use U, V, and A to figure out the displacement. So A, V, and U and S. What's the equation there? It will be V squared is equal to U squared plus 2AS. So we'll have 0 squared is equal to 60 squared plus 2 negative 3s. When we simplify this, we'll actually have 6s is equal to 3,600. Then we have s is equal to, let's see, 600. So the displacement at time 25, so right back here at the back, should actually be 600. And that's it. Should be something like that. I think that's the end of the video.